I thought it would be useful to go through one of these problems, and perhaps I'll end up going through all of them, creating a key via video in addition to showing you the key on the Canvas site. So what I will do is I will step through how I would analyze these spectra, and hopefully that will help you with subsequent problems. Sorry about that. So let's look at the NMR first. Now, before we even look specifically at the NMR, I want to focus on this particular sentence. So I gave you this sentence because there's a lot of overlap in this particular spectrum. So if you look at the integrations, and remember, integrations are the number of protons that give that particular signal. There's one at 7.28 that's an exchangeable proton. Exchangeable means some kind of group that can hydrogen bond. Exchangeable means exchangeable with deuterium. So if you were to add a small amount of D2O to this sample, that particular proton signal will disappear because the D, the deuterium, would replace the hydrogen. So that means there's likely more like a 1, a 3, and a 2 here. And remember that in this region of the NMR, that's going to be aromatic protons. So we have likely 5 aromatic protons and something else on top of it there. Then we have what looks like to be triplets and triplet. So I'm going to go back and forth between the spectra and the table to show you how I would fill this in. And consider we have 4, 2, 2, 2. What I'm going to do is separate this into, for this one, 1, 3, 2, 2, 2. And I'm going to have A, B, C, D, and E. When you see in papers, for instance, that are highlighting NMR spectra, you often see this kind of labeling in order to specifically differentiate the signals and represent them on the final structure. So the integrations, if we go back up, 1, 3, 2, 2, 2. It's always useful as a check to add up that number of protons from the integrations to make sure it matches the formula. So 10 and 10. I'll get back to the units of unsaturation in a second. Multiplicity, if unknown, write multiplet. So this is going to be a singlet. This is going to likely be a multiplet. So if you look here, where above in the full spectrum it said for integration, there's a couple of things going on here. So I'm going to write multiplet. This could be, there could be this right here, could be a triplet, but it's overlapped, so it's difficult to tell. Either way, whether you write multiplet or triplet, I would accept it. And then this is a doublet, or depending on your level of education with NMR, this is sort of a complex doublet or a doublet of doublets. So I'm just going to put the DD down here. Whoop, wait, hold on. Going back up. See? I was getting ahead of myself. I wanted this to be a doublet of doublets. And these are going to be triplets. And then chemical shift, these are all going to be around 7.28, 7.25. And then let's change that one to be a little bit lower. And let me change this to be smaller. You may be wondering, oh, I didn't know professors made mistakes. Well, sometimes we do. So that's 7.18. I'm also not the best at writing with an Apple Pencil on an iPad. Whenever you're writing these chemical shifts down, they don't need to be exact. If you put them out of order, I also don't care. So remember, triplet here and triplet here means that those are going to have two neighbors. Now, one thing that I want to also mention up here is that these two types of protons, they rarely split or get split by neighbors. They can be, and you may have learned that they can be, but one of the issues is that they hydrogen bond. And when you hydrogen bond, you're shuttling those protons back and forth, so it's hard for them to recognize that there's other neighbors nearby. Carbon NMR, you're looking specifically for the number of carbon types only. You may have looked at this and said 1, 2, 3, 4, 5, except that if you look all the way up here, you've got some overlapping peaks. So there's actually 1, 2, 3, 4, 5, 6. And I'm going to erase these down here. So there's a total of 6 different carbon types. This will come into play when you're creating a structure that will likely have some symmetry, considering we have 8 total carbons in the formula. So speaking of which, let's go back. So if we look at the units of unsaturation, 8 times 2 plus 2 minus 10 over 2. So 16, 18 minus 10, 8 over 2. That's 4 total units of unsaturation. And considering that we have aromatic protons here, that's likely going to mean some kind of aromatic ring. Not definitive, but likely. So now that we're going to be going to the IR spectrum, we can look at some specific IR absorption. So we want to look at these, and probably this one, maybe this one. Whenever you're looking at an IR spectrum, everything below 1500 we generally ignore. It's the fingerprint region. There's a lot of things typically going on with the fingerprint region, so we tend to just ignore it. So again, all you need to do is estimate some of these wave numbers. So that's 3300-ish. If you have looked at either an online source or you looked at the videos that I've created for you, this would probably be in the strong category and broad. And the identity of the bond, if you look at a table, this is going to be an OH. And we have an oxygen, so that makes sense. We've got something at about 3050. That's this one. It's medium, sharp. And this is an S, it's in the range of an sp2 hybridized CH. The other two are about 2950 and 2900-ish, both medium. Both sharp or sharp-ish. And these are going to be sp3 CH. This one, it's weak, but I think it's worth using. This is about 1600. And then we have one just about 1500. This is weak since it's the upper part. This is medium. And these are both sharp. And in these range, we're talking about carbon-carbon double bonds. And since we have the likelihood of an aromatic, I'm going to say that these are also aromatic. If we get to the mass spec, now, based on what I'm seeing in terms of comments, many of you have not seen or have seen very little of mass spec, and that's one of the things that we've sort of worried about, is that students have a variety of instructors. I teach mass spec, not all do. So what you're looking for is the highest mass peak here, which is 122, should correspond to the molecular weight. And for CH810O, that's 122. So you mark this as an M+. Now, you don't have to analyze all of the peaks in a mass spec. So what we're going to do is we're going to look at 92, and we're going to look at 91, and maybe we'll just look at those for now. Massive fragment loss is 30 and 31. So if you were to look at this, you can add up a number of atoms together from a structure in order to get that. So 30, probably CH2O. CH2 is 14, oxygen is 16, and maybe here CH3O. Do you have to identify the exact fragment? No, you do not. So now we need to start coming up with a structure. So let's go back to the NMR. The NMR is always going to give you the most information. So I said we likely have an aromatic ring, and based on the IR, we have an OH. So is there a way that I can create this by and then adding 2 carbons to this to create 2 triplets? So yes, I can do that. So if I do a CH2 here and a CH2 here, keeping in mind that it's very unlikely that the OH is going to split. So you don't necessarily need to count this as neighbors to these two. So this one has 2 neighbors, and this one has 2 neighbors. So that could be a triplet pair. You can also look at the chemical shift. So the chemical shift for a CH2 next to an aromatic ring is in the 2 to 2.5. And for this one next to an oxygen, this is going to be 3 to 4. So do we see that? Well, I say 2 to 2.5 and we see 2.7. These limits are not hard limits, so you can have things above and below. So it still would technically fit. And then does this aromatic ring match the number of protons we see above? Well, if you take out the exchangeable proton and do 3 and 2, you can get an aromatic ring. So let's say that we just have a monosubstituted aromatic ring. We would have a total of 5 protons. Because we don't have a significant electron withdrawing or electron donating group here, these 5 protons are going to be very similar. They might really be on top of each other. So as long as you have a total of 5, you're likely going to have an aromatic ring like this. In the real proton NMR, I think these will be the ones that are slightly upfield. So those two are going to be the C, and then B are the remaining 3. A is the OH, and then D at 2.7, and E at 3.7. So let's write this all out down here. And you could look at the written key online when we get it up to show my description. But again, we're talking about A, B, C, oops, D, and E. And that's it.